Hello friends, today we'll discuss about a data structure called segment tree. Segment tree is a data structure which provides efficient range query operations in an array. Let's learn it through a problem where you are given an array A with integer values of size n. You have to answer two types of queries. One is you have to answer sum, print the sum in a given range L to R, and you have to update the value at ith index with value x, and these two operations needs to be done in big O of log n. One thing to mention here is this update query is not a range query, but segment tree can be used where update query is also a range query. We'll look into that in a later video. Now let's discuss the structure of segment tree. So segment tree is a binary tree which stores the information of interval or a segment, you can say. So the root node will store the information of whole array. Let's suppose you are given an array of size n, so 0 to n minus 1 elements information. What is the information here? Here, since we have to do sum, the information is the sum of this complete array. Let it be S0. Okay. Now we'll divide into two equal halves. Okay, 0 to n by 2 and n by 2 plus 1 till n minus 1, and store this the sum of this segment in this node. Let's say it is S1, and similarly this S2. We'll keep on doing this, repeating this until the size of the segment becomes 1. Segment size becomes 1. Okay, let's see what will be the height of this binary tree. Since at each step we are dividing this array into equal halves, so the height will be big O of log n. Okay, now see how many number of nodes it will have. At level 1, that is at the root level, we'll have 1 node, then 2, next level, then 4, and at the last level we'll have 2 to the power seal of log n. Why C? Because since it's a memory, n won't be the exact power of 2. We have to take C. I'll tell you when this worst case will happen. Let's suppose this is the last level. If suppose this is the last level, then last level minus 1 will have less than n nodes. Why? Because if it would have been n nodes at last level minus 1 level, then we would have stopped there only, because we have already reached the segments of one size. Okay, so let's say this is first. Okay, this is a geometric sequence. This will clearly less than this number. Why? You can use the sum property of GP. Now we'll do some simple mathematics to use this equation, and this equation we'll put here, and 2 to the power minus 1 plus 2 and 4n. So number of nodes will be clearly less than 4n nodes. Okay. Now let's see for a given example array A, this array of size 6, how the segment tree will look like. And we'll do sum only. For 0 to 5, the sum is 21. Stored this information. For 0 to, then we divide it by 2. So 0 to 2 till this, 3 to 5 this part. Okay, and what's the sum? 0. We have stored this information. 3 to 5 stored this information. Then again we divided by 2 left child, 0 to 1, 2 to 2, and then 0 to 0, 1 to 3. Here we stop. Why? Because the segment size is now 1. Segment size is 1. Similarly, segment size is 1. Segment size is 1. Now we have seen how we can construct the segment tree. Let's see how to find the sum. Let's suppose you have to find answer for this given range L to R, and you are on the node which stores the information of the segment SL, SR. Okay, there are three things which can happen. First is SL and SR, the node on which you have, has same segment range which you need to find. Then you can just return the node value. Second thing which can happen is, let's suppose you are at given node SL, SR, and you just need to find in that the query you are given lies inside this range SL, SR. So it will be either in the left child or right child. Okay, this is the second option which is possible. Third option is the range you have to find lies in both left and right child. Okay, so what we'll do, for this case you just need to return the value. For this case you just need to recursively call for the left or right child, recursively call for left or right according to the segment in which it lies, the range, query segment in which it lies. For this you need to call for both left plus right, and at the end sum the left and right answer, left and right child answer. Okay, now let's see an example. Let's suppose you have to find sum in the range 1 to 3. Okay, we'll start with the root node. We can easily say 1 to 3 lies inside 0 to 5. We'll divide in 1 to 3. We'll check 1 to 3 lies in left or right. Since 1 till 2 will lie in the left side, and 3 till 3 will write in S. We'll call for both the parts. We'll call now for 1 to 2 and right side 3 to 3. And again we can check that 1 to 2 completely lies inside 0 to 2. We'll check whether it lies in left side or right child, and we'll call 1 to 1 for left, 2 to 2 for right, and keep on doing it till we reach the last node. Here, since it matched our the query range, we'll return this value 3 to it, and this 3 to 3, and this matched with this range, so we'll return -5 to it, and finally sum these two values. Okay, now from right hand side again we'll find the range 3 to 3 lies inside this. Then we'll check whether 3 to 3 lies in left or right child. It lies in the left child, and finally left child. This will return 6, this will return again 6, and this will return 6 again. To this is -2, answer will be -2 plus 6 equals to 4. This is 4. Okay, let's see the time complexity of the sum queries. So at max we have log n levels, so we'll be going in L levels, log n levels. We go of log n. Let's see how many nodes we process at each level. How many nodes we process? If at each node, if we have taken this type of decision, that is this condition becomes true, then we won't be calling any recursive call, that is it won't call any other node. If this is true, then we will be calling one node. If this is true, we'll be calling two nodes. Okay, now this one node can call now two nodes, at max two nodes, and this two nodes can at max call 3 or 4 nodes. So till now what we have got is that at any level we can have 2, 3 or 4 nodes. So let's say if there are two nodes, then it will lie again in this case, and this case give rise to 3 or 4 nodes. Let's suppose we are at level where there are 3 or 4 nodes. We can take anything. Let's say we have 3 nodes. Okay, 3 nodes. Then this case only, let's say we are at this level and we have these 3 nodes: first node, second node, and third node. So this can internally call this, and this nodes. These sum queries are continuous queries. I can clearly say that this node, this particular node, second, won't call its child, because the query range, if there are 3 nodes at this level, then this middle node will be completely in the given query range to be answered for, let's suppose, L to R. Then this will lie completely inside L to R, because some queries are continuous. So we'll only have the new recursive calls for the leftmost and the rightmost node. That is, again, there are at most 2 nodes at this level which can call recursively, which can result into 3 or 4. This is true for 4 nodes also. You can check it. So what we say is, at each level we process at max 4 nodes. At max 4 nodes. So the complexity of this segment tree sum query becomes big O of log n. Okay. Now let's see update queries. What we do, let us suppose we have to update the value at ith index with value x. Okay. So what we do is, we update the leaf node which stores the value of ith index. Okay, and then we recursively reconstruct the binary tree as we have done previously. Let's take an example. Let's suppose you have to update second index of the array with the value 3. Okay, we'll go till the leaf node which stores the value of index 2. So we'll start with 0 to 5. 2 lies in the left side. We'll go to left, and we see that 2 lies in the right side. We reach the leaf node which has which stores the value of second index. We update this value to 3. Okay, then what we do is, we go back to the root parent node of this node. Since we already know this child value, it hasn't been updated, we need not to go to the left child, and so the answer will be updated to 0 to 8. 5 plus 3, 8. So I'll update right here, 8. Now again we'll go back to the parent of this node, and since this right child hasn't been updated, only the left child has been. 8 plus 21 equals to 29. Okay, now we have updated our segment tree according to the new update. Let's see what's the time complexity. For time complexity, clearly we can go at max log n levels. How many nodes we process? Since this ith index on a given level will always be present in only single node, so we'll be processing 1 node at each level. You can clearly say, in this case only, the 2 either can lie on the left side or right side. It cannot be on the both side. So we went to left side because it lies in left side. Here it lies in the right side. We went in the right side. So at max 1 node will process. So this is big O of log n.